Mango Math presents Billiards, a pre-algebra game. Billiards is a pre-algebra game that falls under the idea of measurement or ratios and proportions. And it's a game that has students recognizing proportion relationships between two quantities and then deciding what that relationship is. Billiards has some math terms to help increase understanding, and those are line segment, a section line bound by two endpoints, and ratio, a comparative value of two or more amounts, and can be written in these three different forms. The supplies that are provided in the pouch along with your information sheet and directions will be a billiards game board, a 12-sided dice, a dry erase marker, and eraser. To do this activity, you first want kids to explore the relationships between the sides of the billiard table and the direction the ball is going to advance in. So we want the kids to first think about the different corners of the billiard table, and I've labeled them A, B, C, and D. Now if I make a rectangle off of the corner A being the right or the left corner, and you measure across a certain amount, and then you go up and you create a rectangle. If I hit a ball from that corner A in a billiard table, which does not have pockets like a pool table does, what corner will that ball end up in if it's delivered in a 45-degree angle? So I'll explain how that works. So let's say we first make a table that is a 5 by 10 table. We write that down. Its width is 10, its length is 5, 10 by 5. And we are then going to hit the ball from the corner of point A and hitting it at a 45-degree angle. It's always going to be hit at that 45-degree angle. Each time we play this game, we want to make sure that we are dissecting each one of those squares directly in half with a diagonal line or line segment. So if we hit that ball from corner A, it's going to go up and hit that spot right there, which is at the 5-5 spot, and then bounce off that at a 45-degree angle and end up at the pocket of D. And that's if we're hitting it square on and it goes directly the way it should go. It should go directly into D. Now we want to look at what path it took. It took that first path, and that went to that 5-5 point, and then from the 5-5 point up to that corner point of 0-10. So we then hit that, and we have two lengths of paths, or two paths it took. So we write in the 2, and what corner it ended up with was D. Now that's our first one, and we're going to start to notice, do this activity again, and we do a table that is 6 by 10, and we hit our ball again from that point A at a 45-degree angle. We get our ball, it goes and bounces at that 5-5 point, and then it goes up and bounces off of a 2-10 point, comes back down to a 0-8 point, then comes back down to a 6-2 point, and then it comes down again, lands on a 0-4 point, and then goes up to a 4-0 point, and then goes up to a 4-0 point, and then goes up and finally hits into that corner at corner C. So it took a much longer path to get to the corner, and we measure each length line segment before it gets against the wall or hits the wall, and we have 7 line segments that it created. Each time I talked about each line that it created, and it ended up in C. So we're starting to establish a pattern. I've got a 10 by 6 or 10 by 5. It took a path of just 2 steps and landed at D. A 10 by 6 took 7 steps and landed at point C, or corner C. So let's look at, the kids can continue to look at those lengths, but let's look at a different type of rectangle. And let's say we made a 2 by 2 rectangle. If I hit from point A at a 45-degree angle, I get directly to the corner that would be in relationship to C. So I only have one path, and the corner I hit is C. If I do this activity again and I have a 4 by 4, and I create a path, it just continues on, a straight one line segment, and it ends up in C again. So if I create the next one, which is a 7 by 7, if I shoot from corner A at a 45-degree angle, how many paths am I going to have? Can we make a prediction based off of what we learned so far? Yes, it's going to continue straight up, and we're going to have just one straight line. And we get in there, and it's going to still end up in point C. So any square number, regardless if it's a even or odd number, is going to have just one line segment that bisects it at a 45-degree angle, and it always end up in corner C. So we figured that out. So you could write actually even a proof that this is always going to happen if you have a square rectangle that's a square on a billiard table. It's always going to go that way. So let's look at a different size triangle. Let's go with a width of 12 and a length of 1. So we make a rectangle that size. Now let's look at the path the ball will take if hit at a 45-degree angle from corner A. We have that length, another segment, another line segment, another line segment, again, 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 and it just bounces its way up until it hits the corner D. So the path it took for a 12 by 1 was that it took 12 hits, or 12 line segments, to get up to the top or get to the final corner. So let's look, we got to corner D, so let's look at a different size table this time. Let's look and extend it to a 12 by 2, and let's see how this path differs than that original path we had. So if we hit again from corner A and we take the path, we start to see that it takes a little bit different route, and we have a 12 by 2, and it took 6 hits or 6 line segments to get to corner D. So let's look at another one. Let's look at a 4 or a 12 by 4, and what path is that going to take? And that goes up this way, where you have 1, 2, 3 line segments, and it ends up in corner C. So it ends up in a different corner. But let's look at the numbers that we have here. We have a 12 by 1, I have 12 hits. I have a 12 by 2, and it hits the ball 6 times. And I have a 12 by 4 that hits the ball 3 times. Do you see any relationships there between the numbers? 12 divided by 2 is 6. 12 divided by 4 is 3. So there's some relationships there, aren't there? So the kids can continue looking at the relationship between a width and length that is divisible by each other, or one's a factor of the other one. So that can give you some ideas on how to look at with their billiard table. And let's do one more. Let's look at some different widths. We have a 2 by 1, and that path took 2 line segments and ended up in corner D. What if we did a 3 by 2? And notice it took 4 different lengths but ended up in B. And let's look at a 4 by 3. 6 lengths ended up in D. And let's look at a 5 by 4. Where do you think it's going to land? Path of 8 and ends up in B. Let's see. That's true. So you're seeing a relationship between these numbers. Is there a ratio that's going on here? Is there a pattern that's being followed? If we have a 6 and a 5, we would have path of 10 ending up in what corner? I'm going to guess D. Correct. That's correct, because that's the path it follows. So looking at these, there's a pattern it follows. You see the paths, it's 2, 4, 6, 8, 10. It's going to D, B, D, B, D. Up above is 2, 3, 4, 5, 6. What's the relationship here? Do you see any patterns that are going on? Can you make predictions if I say, what is the rectangle, what corner, or how many paths will be taken if I have a 10 or 100 by 99? What if I had 101 by 100? Look for patterns. They are there, and have kids start predicting what's going to happen when they create tables like these ones that are created. So they can do it on different graph paper. The graph paper provided isn't large enough. If the billiard table for you isn't large enough, get a different graph piece of paper and see if you can check out different sizes. They have to draw every line segment they can. Make sure you use like a ruler when drawing line segments, just to make sure that they are accurately following the right path at a 45-degree angle. Otherwise, they can get off on their sequencing. So to play the game, after the kids have been experimenting with the different rectangles and the relationship they have, the kids will start a game in which they will each select a corner. Brian has B, C, and Dana has D. Nobody will have corner A because that's going to be the corner that you hit the ball out of to begin with. So they're going to select a width and a length. So let's say they roll the ball and they get 12. So they're going to say a width of 12 and a length of 1. And they will make that how they want to on their board. And then they will create their path. It gives them 12 and it ends up in B. So Brian got the right one there. So if Brian was going first, he would gain, and he got the corner that he wanted, he'd gain a point because that's his corner. If we do another roll, and let's say it's Dana's turn, and we roll it and we get a 3, they now have to come up with a rectangle using the 3 that's going to get the ball to land in their corner. So they create, let's say they create a 3 by 9, and they then hit the ball and they get into the corner that is CC's. But Dana was the one that drew it, her corner ended in CC, so CC would get the point because it ended up in her corner. So that's basically how you play this game. The student will roll the dice and draw a rectangle that gets them into the corner that they want the ball to land in, which is their corner, so they can gain a point. You might have to set some rules on that. They can't always have a width or length that is 1, so they have to start thinking about what they're doing beyond just a simple 1 that would get them to go in a fairly easily predictable outcome. So have them guess different sizes to get the ball to end up in their corner. So it's a lot of thought process in this activity. A lot of patterns that they can recognize, and a lot of thought on how am I going to create a rectangle so that the ball ends up in my corner. So some guided questions to promote critical thinking. This is a very thoughtful game. There's a lot you can do with it. Don't feel intimidated by not knowing what the right answer is. You might just discover the patterns on your own as well. So just enjoy the activity, seeing if you can create tables where it goes through the most points, or it gets in the corner you want, and so forth. Just play with the tables. So here's some guided questions to promote critical thinking. Which table does the ball have the most simple path? What is special about the shape of that table? So that was one of the demonstrations I gave in the display. It was a square. We'll create just the most simple path, which is just one straight line. On which table will the ball never cross itself? So are there tables where it just always goes in one path and doesn't come back down the board, so to speak? It just goes up or over in one direction but never crosses itself. And will a ball hit from the left bottom corner end up in any of the 4 corners? Explain. So if you're hitting a ball from the left corner, which is where we've been hitting it, what if we changed over to the right corner? So looking at the different corners, does it make a difference on where the ball goes? And on which table does the ball have the most complicated path? Is there a path that you can divide every single square in half with your 45-degree angle? What corner would the ball end up in, a 99 by 100 or 100 by 101? And those were the ones I left blank on that pattern we created earlier. So going back and looking at that pattern and seeing what will happen on a 99 by 100 board and a table and a 100 by 101 table. So think about the different size tables, think about patterns, and think about, once we've figured out this pattern, can we predict what a much larger table would look like. So enjoy the activity, a lot of thought in it, and it's a lot of fun to do.